By now you probably recognize that this chapter is much shorter that we're going to cover just because I didn't do that many slides. So you can see this visual on here. It's a kind of interesting way to look at a Dobson unit. What does that say? So it gives you the global average ozone in Dobson units. Yeah, okay. So using what, dimes and pennies. All right, so I'm pretty sure I just pulled that off the NASA website because they're the ones that monitor this stuff, as you saw in chapter 1. Okay, the goal here is to just sketch out some of the prominent reactions that happen for ozone depletion. The book does a lot more detail. So what I did with this is just sort of consolidated it into 3 classes: aqueous phase reactions on or inside of the interior of the polar stratospheric clouds. And then we talked about acid, base, and redox. Then chemistry that you're very familiar with. So the free radical chemistry that takes place in the gas phase. And then mechanism 2 is of ozone depletion that we talked about before, is the primary mechanism because of insufficient UVC. So you can see all those notes there. So let's just go through some examples of some chemical equations there. And this is just an overview, because I think it's all we need to kind of get the flavor. So we're doing letter B, prominent chemical reactions. And if you need to go back and review, I didn't put this as part of the review problems, but if you want to go back and look at acid-base chemistry, like Bronsted acids, Bronsted bases, conjugate acids, conjugate bases, that's useful information to look at. I think we're going to use that more when we actually do the chapters on water chemistry, where that'll become more important. But if you want to look ahead and just remind yourselves of what all that means, this is really just touching on it. Same goes for redox. We're not going through the definitions of oxidation, loss of electrons, the definition of reduction, gain of electrons, and how you balance them. There's a whole process there. This is just an introduction. So, Roman numeral number 1. Aqueous reactions, again, these are not taking place in a beaker. These are taking place up in the stratosphere inside of a polar stratospheric cloud, a PSC. So, and only over the Antarctic. And these are just examples. So we have aqueous reactions, write out the full headings if you want to. And then we'll do acid-base, examples of the acid-base ones. Now, I'm just going into some of the prominent ones. In fact, this one I'm not even describing where it comes from in these notes. This molecule comes up from time to time, and this is called chlorine nitrate. Where does that come from? Well, that comes from a pollutant. Remember what we're doing here, primarily talking about anthropogenic, man-made, human-generated chemicals. And there's a chemical reaction that forms that. And if you want a reference to that, that's on page 29 of your book. I don't want to rewrite everything from the book. I just want to give the highlights. So this reacts, this is a gas, and when that comes into contact with water from the PSC, so you can write that here. This is the chemical reaction that happens. You get HOCl, which if you've had Gen Chem and you had to memorize some acids, that's called hypochlorous, I think I spelled that right, acid. And then you also get HNO3, also aqueous, and you probably recognize that. That's nitric acid. And I'm going to label this chemical equation 1. You can make a note here that when this reaction happens, yeah, that ultimately can lead to further ozone depletion, but if this happens in a cloud and then that precipitation in the cloud rains or snows and falls back down, this is where you get acidic deposition or acid rain. This is one place where acid rain can come from. Another one, which is a much simpler reaction, is it is possible in the stratosphere to generate hydrogen chloride, which that's what it is as a gas. You would be used to seeing HCl, AQ, hydrochloric acid. Now, where does that come from? That comes from a chlorine radical, free radical, abstracting, I think that's the term your book uses, hydrogen from some other source, and I put a page here. That's page 28 of the book. Okay, we're just touching the basics here. So, in the presence of water, just like on Earth, on the surface of Earth, like in a lab, if you've ever had the pleasure of getting some hydrochloric acid fumes up into your nose from a bottle of concentrated hydrochloric acid, this is what happens, and it's kind of a painful experience. And I'll call that equation number 2. And I have a sneaking suspicion I didn't press the on button. Did I do that? Okay, sorry, I keep coming back and checking. It's just my anxiety. Not really. Just want to make sure I'm not talking to a non-recording camera. So those are 2 examples of acid-base reactions that happen. And we'll go through this in more detail in the aquatic chemistry unit. But this just kind of gives you an idea of, okay, these reactions actually happen. And so that's some samples of acid-base. And let's, if you want to write this out, if these are oxidation-reduction reactions, and we combine those to call it redox. One example. Remember, these things can't be considered ice, so you produce some Cl minus. That can react with something else. And you can produce chlorine gas. If you know anything about the history of chlorine gas on Earth, that was manufactured in World War I in large quantities, I think primarily by the Germans to use in trench warfare. So you get an idea of how dangerous that is on the surface of the Earth, but that can then be released into the stratosphere. Where it can then participate in ozone decomposition in subsequent reactions. So you have to think about all these things as a cycle or a sequence of chemical reactions rather than just one happening at a time. And then in this particular example, we also produce hydroxide, which is very, very basic. So H plus is what makes something acidic. OH minus makes something basic, as you might recall. And I'll call that equation 3. And I think that's all I wanted. Oh, yeah, I'm just going to say this here. So, in this particular example, let's see. Chlorine is called the reducing agent because it is oxidized from -1 to 0. So it's called the reducing agent. This is called the oxidizing agent. That is unimportant for this chapter. This is just to show you some basic chemistry principles apply here. And then that gets reduced. It's the oxidizing agent, so HOCl oxidizes Cl minus reduces. Okay, so this is reduced and it ends up becoming OH minus. And the only thing I want to add here is a note. Get it down a little lower. Again, this was really just because I thought it was interesting. If you take equation number 1 plus equation number 2 plus equation number 3, meaning you add them all together with a very standard reaction, H plus OH minus forming water, and you can convince yourselves of this, and I'll call that. So if you do that, if you simply add up all those equations, so 1 plus 2 plus 3 plus this one, if you want to call that 4, but I call the result 4. What you end up getting is this. It's kind of like Hess's law, where you're adding reactions together. I think one of the reasons I'm showing this is I think one of the graphics, maybe that I first used, had this as an example. So you get, my goodness, you get chlorine nitrate plus hydrochloric acid gas, and that can produce chlorine gas plus nitric acid. Just an example. There's no way you would memorize this, but just to show how all these things are tied together. Okay, the second couple of classes of reactions, we've done a bunch of these already, so I'm going to kind of whip through these. So just give me a second. If you're looking for something to do while I'm doing this, or just hang out for a second, we're going to do an example together, a case study on a molecule called Freon 12. It's a molecule that is a CFC. It was one of the most common refrigerants used. I think it still might be used. I'm not sure. A lot of countries have banned it. Maybe that's something to look up. I don't remember. But that's the industrial name. It's called Freon 12. And one of the things I had you do is look up what's called the SDS sheet, the safety data sheet. If you're older like me, you might remember those called MSDS sheets, material safety data sheets. It gives you all the information about a chemical, including its safety hazards. So if you're just kind of hanging out and want to look up the SDS sheet for Freon 12, go ahead. If you're not, don't worry about it. Okay, so the second kind of reactions, those are aqueous phase reactions we did there. Well, we've already talked about these, so I can do these quickly. So free radicals that take place when we generate chlorine gas, which is another reason why I mentioned those chemical reactions. You generate Cl2, and you put that in the presence of ultraviolet light, and you get 2 chlorine radicals. And where does this specifically happen? This is kind of cool, I didn't know this. During the spring, during the polar vortex, chlorine gas accumulates at the very edge of the vortex. And this is in, early, that's supposed to be early, spring. Okay. Other things that can happen is hypochlorous acid in the gas phase can also split to form hydroxyl radicals and chlorine radicals. And remember, these are what then drive the ozone depletion. So not these themselves, but the free radicals. And that's where we get into, for the ozone holes specifically. Remember what we're doing here. These are all things that lead to Antarctic ozone holes during the early, during a specific time period at a low temperature contained by the polar vortex. And it is specifically with mechanism 2 from chapter 1. And there's a nice figure in your book, which I'll reference here. So just to give you an example, so step 1 is some radical generated from somewhere. Shouldn't be using the dots, so step 1. So let's just take a chlorine radical that's produced by photolysis that came from chlorine gas, that came from an aqueous reaction in the polar stratospheric cloud. See how this gets complicated? Okay, so the free radical extracts some oxygen from ozone, and figure 2-4 in your book lends a little bit of insight into that. I just want to look at that figure. Oh yeah, okay. And the figure 2.4 shows the concentrations of some of these at different locations. So you can look at that figure yourself. I'm not going to try to redraw that here. Now in this particular example, step 2 has, well, 3 components to it. There's 2A, 2B, 2C. Again, we're not expecting this to be obvious how this works. So what happens is, with the next thing, you produce the ClO radical, chloroxy, I'm not sure what that's actually called. When you read your book, I guess that's called I'm not sure what that's called. Pardon me, I should know that. Is the second step, 2A, 2 of those combine. And they actually just simply bond together. So 2 radicals, that happens all the time. 2 radicals, they're unstable, they each have a lone electron, so they just form a bond. And that's given a specific name. That's called a dimer, when 2 of the same thing bond together. And this one, I do have the name written down. Dichloroperoxide. It's a great name, because if those were hydrogens, that would just be hydrogen peroxide. So this is dichloropyroxide. And the comment I want to make here, and this is kind of important, this happens only at low temperatures. And the rest of it's actually pretty straightforward. So, well, remember how these reaction mechanisms work. You produce one thing, that becomes a reactant, that does something else. So the next thing that happens is, well, the dimer, ClO, now it doesn't do just the reverse of this reaction. What it ends up happening is a chlorine free radical breaks apart. So both of these are now free radicals. There's no way you would know this. This is not that obvious. So then, in the last step, is where you get your next oxygen being produced. And a note on the side of this, this takes about a day to occur under these conditions. Now, remember, when we do mechanism 2 always has the same result. So always, always, always has the same result. You have 2 ozones producing 3 oxygens. That never changes. Mechanism 2, you follow the steps, and this is what you get. If you add this up the way I've written it, it does not happen that way. So the only thing we have to do, and this is a legit move, if you're going to make this work, take step 1 and multiply it by 2. So put a 2, 2, 2, 2, add all that up and convince yourselves that this is what you get. If you need to. If you need to. Okay. Let's see, what do I want to do with this one? There's one comment I'd have here before this. I think we need it. It may help, because especially when we do some kinetics later on. So this step 2A, right here, this happens at low temperatures, and this is a very, very slow part of the reaction. So you might remember from kinetics. I'm just going to add this as a note. So step 2A is what's called the rate determining step. In other words, that governs how fast the reaction goes. Again, we're not doing a ton with kinetics, but I think it's important to at least note this. And also, when you write the rate of a chemical reaction, that is a specific step in a mechanism. So the rate of step 2A, this is, if you look at the kinetics review, this will make sense. It's a rate constant, that's what the little script K is, a rate constant, times the concentration of the reactant. In this case, it is a second order reaction. What does that mean? So ClO, this step is a second order reaction. A key takeaway from this is the rate of ozone destruction is quadratic. It's a squared term. In practical terms, that means if a lot of these ozone depleting chemicals get into the atmosphere, they actually accelerate the rate of ozone production, not in a one-to-one fashion, but in a one-to-squared fashion. That's really the only thing I wanted to mention there. Okay, I'm going to stop this lecture now. The next thing we're going to do, the last one, is a case study problem. And in fact, oh, I'm sorry, I need to finish this part. You can tell I didn't rehearse this one very well. The parting shots that I have. Fine. There's just a couple of points I wanted to make there. So denitrification is just a definition. It means that the removal of NO2 by reaction, you can see that there. I erased all those chemical equations. But when you remove nitrogen oxides from the atmosphere, that's typically a good thing, because usually those are pretty severe pollutants. And we're going to talk a little bit more about that, a lot more about that next chapter. But that's the removal of nitrogen dioxide, actually any nitrogen oxide, NOx, if you remember that one, by the reaction of okay, you can read that for yourself. And then step 2A is second and the rate determining step. I forgot I had a note there. Part of what I'm having you do on the homework is unpack the following statement. This is one of the best one-sentence statements I think I've ever read in a science book. And that goes through and explains almost all of the details of the ozone hole formation at the Antarctic in a specific set of months by the polar vortex containing it. So one of your homework problems is to unpack that statement a little bit more precisely. I'm not going to sit here and read that to you. Okay, let's stop the video now. What we're going to do, and you can do this without the next video if you want to do this for starters, we're going to do a problem together. Now, when I teach this in class with a bunch of people, I would just flash this up on a screen and say, break up into your little groups and work on it. Then write your answers on the board and let's discuss them. We're obviously not doing that here. So if you want to jump ahead, we're going to do problem 2.4 as a case study of Freon 12, like I mentioned before. So if you don't even want to watch the next video right away, just go to the slide and do all of this on your own. That's actually good to see if you understand what's happening here and can apply a lot of the concepts. But then I'm going to stop the video and then we'll come back and review some of that. Some of it I'm not going to do in depth that you can finish on your own, okay?